Good morning and welcome to the lecture number 8 of this video course on advanced hydrology. In the last class we looked at the derivation of the Green-Ampt equation, which is the infiltration equation, and what I would like to do today is just go over it quickly so that we understand the basic steps that are involved in the derivation. So, we come to the tablet here. We are looking at the Green-Ampt method, all right, and what we said is it provides an exact analytical solution with certain approximations to flow situations and Richards equation. The Green-Ampt equation is a combination of continuity and momentum equation, and how we derived it was that we first looked at the simplified soil moisture profile, and then we took a cylindrical volumetric element, and then we applied the continuity and momentum equation to that. So, if you look here, you see that this is the cylindrical element. The length of this wetting front is L, and its cross sectional area of the cylinder is A is equal to 1. As the rain is falling, water is infiltrating into the ground and the depth of the wetting front is increasing. Then we defined various parameters that are involved. I would not like to go over them again. And then we applied the continuity equation, in which we said that the cumulative infiltration at any given time is nothing but L times delta theta, where delta theta is this quantity eta minus theta I. And we had seen earlier in the first few classes that the momentum equation for this kind of situation is nothing but the Darcy's law. Okay. So, we started with the Darcy's law, which is equation number 2, and then we utilized the concept of various forces that are acting in this particular case, which were suction forces and the gravity forces. So, corresponding to that, this energy H we said is the sum of two things, all right, and then we derived the expression for small f using this, considering two cross sectional areas 1 and 2. 1 is at the ground, which is the datum, and 2 is at the depth of the wetting front. Okay. Then we continued further. The head H we said is the sum of these two things, as I said earlier, all right, and once we derive this equation, this is called the momentum equation, equation number 4, which we found out. So, now what we did was we combined this momentum equation with the continuity equation, which is represented by this essentially, okay, and we put it all that and then separate the variables, perform the integration, and the final equation which we get comes out in this form, okay, or rather in this form, okay, equation number 6. So, equation number 6 we said is gives you the cumulative infiltration as a function of psi delta theta, and delta theta involves the soil properties, that is porosity and the initial moisture content, okay, and the hydraulic conductivity and as a function of time. So, you see that this equation 6 is a implicit equation and it is non-linear in nature. So, we need some kind of iterative technique to solve it. Okay. We would like to take an example maybe in the next class on how to find the cumulative infiltration given the Green-Ampt parameters. One of the advantages of the Green-Ampt equation is that it gives you a relationship between small f and capital F, that is infiltration rate and the cumulative infiltration. Okay. So, capital F here is the cumulative infiltration and small f is the infiltration rate. Okay. This we had derived already. Other thing we said is one of the assumption was that the ponding depth H naught we took was negligible, all right, in deriving this equations 6 and 7. However, if that is not the case, then all we need to do is instead of psi we just take psi minus H naught, all right, and we replace these psi by psi minus H naught and all these equations, and we will be fine with that. And then what we did is we define another parameter called the effective saturation, which is denoted as SE, and this SE was defined as the available moisture, the ratio of the available moisture divided by the maximum possible available moisture. Okay. And then we found out an expression for SE for the initial conditions in a soil. Okay. For soil moisture theta, the minimum and the maximum limits are theta r, which is the residual moisture content, and the eta, which is the maximum soil moisture content equal to the porosity. Corresponding to those two limits, the SE would vary between 0 and 1. So, this is a convenient way of representing the percentage of saturation or effective saturation in a soil when we are analyzing the infiltration. And then we wrote down an equation in terms of delta theta, the effective saturation, and the effective porosity, okay, because theta r is something which cannot be replaced just by gravity forces. All right. So, for all practical purposes, if we have the values of theta r, this is the equation which normally should be used because it accounts for theta r. Then we moved on and we started looking at the Green-Ampt parameters. Okay. Any mathematical model we have, it involves various parameters which need to be calibrated or the values of which need to be found out. Okay. Similarly, for the Green-Ampt parameters, we said there are 3 or 4 calibration parameters which are involved in it. First one is the hydraulic conductivity K, second one is the porosity of the soil, and psi is the suction head. All right. All these are properties of the soil, and then this theta I is nothing but the initial moisture conditions of the catchment. Okay. And all of these are normally assumed to be constant. So, whenever we apply Green-Ampt equation to find the infiltration during a rainfall event, we assume these quantities or these calibrated parameters to be constant. Many people have conducted a lot of experiments to find out the values of these parameters, and in the book Chow's book you will find a table which gives you the value of these values of these parameters for different type of soils, that is clay, sandy soil, and so on. Okay. For different types of soil, these values are given which are constants. Okay. However, many researchers have carried out some research or additional work in which they have found out that some of these parameters are not constant during a rainfall event. Okay. As the rain starts to fall, if the soil moisture is 0, the soil is completely dry, then the permeability or the suction head or relativity or the relative force which are acting will be different, and depending upon that the values of these parameters will be different. Okay. So, we said that this suction head, some people have found out that this varies as a function of theta or as a function of time during a rainfall event. One of the relationships which we will look today is called the Brooks and Corey relationship. It was established in 1964 and they showed that both psi and k are function of theta. Okay. And the equation which they gave can be written like this: your effective saturation SE is equal to psi b over psi raised to the power lambda. Okay. And I am going to number this equation as equation number 11. Okay. If you look at this equation, okay, I would like to draw your attention to this equation 11. We are trying to find out a relation between psi and theta, that is to say the suction head as a function of soil moisture content, and this equation is in terms of SE, some psi b, some lambda and psi. Okay. So, where is theta involved in this? As you all know, theta is involved in this effective saturation. Okay. If you remember, we had just defined what is the effective saturation. This effective saturation is nothing but it involves this theta minus theta r over eta minus theta r. Okay. So, this is the equation, and any equation which we have, we need to calibrate or we need to find out the parameters. So, in this equation, what are the parameters and what are the variables? As it is easy to see that SE and psi are your variables, okay, and which relate basically your suction with the theta, and your psi b and lambda are the parameters. of this Brooks and Corey relationship, all right, which are constants. Okay. Now, how do we find these values? Before we can establish a relationship between psi and theta, we need to be able to find out this both psi b and lambda, which are the constants in this equation. Okay. So, what they have done is they have given a procedure, a step by step procedure of finding out the values of these two parameters. Okay. So, what we will do is we will look at this procedure of estimation of psi b and lambda, which are Brooks and Corey parameters. Okay. So, I will give it to you in a step by step procedure. What is done is a soil sample is taken from the field, that is and it is completely wetted. Okay, that is completely drenched with water, and then what we do is the sample is now drained. Drained means water is allowed to drain or pass through the sample or infiltrate through the sample. And then what we do is we take various measurements while the water is getting infiltrated through this soil sample. So, in the third step, the values of SE and psi, the suction head, are measured at various times or stages. Okay. How do we do that? SE, as we know, is nothing but the soil moisture content, all right. So, we can measure the soil moisture content at any given time in the field, in the sample. Okay. How do we measure psi, which is the suction head? Well, we will not go into the details, but we have very sophisticated instruments which are called the tensiometers, which can measure the suction head or the power of the soil to suck the water, okay, at different stages. So, assuming that we can measure the soil moisture and the suction head at different times, all right, we take the sample, completely wet it, we allow it to drain, allow the water to drain, and then we measure the quantities of your SE and psi. Okay. So, what we have is the data in terms of the soil moisture content and the suction head. Okay. Then what we do is the equation 11, which we had just seen, is fit to this data set. The data which we have thus obtained, which is in terms of SE and psi, to find the parameters psi b and lambda. How do we do that, or how do we find out the parameters, all right, of a two dimensional problem where you have x and y, you know, only two variables involved. Okay. It should be easy to see. If you have data or two variables x and y. Okay. So, x is the independent variable and y depends upon the x, all right. So, what we do is, let us say we have taken certain observations of x and y. Okay. Let us say they look like, or you just plot them. Okay. If you want to establish a relationship between these observed data, we look at the pattern, all right. If it appears linear, then we try to fit a line or a linear curve. If it appears a non-linear curve, then we try to fit a non-linear curve. So, let us say that if it is it appears like a straight line, then you just fit a straight line through them. Okay. Graphically it is easy to understand, but mathematically also there are equations which we can use to find out the parameters of this line or this model. What are those parameters? It is nothing but the equation of the line is y is equal to mx plus c, as you all know, and the parameters are m and c. What is m? M is the slope of the line and c is the intercept. Okay. So, once we have found the value of m and c, we have determined the equation of the line, or we can find out the value of y given the value of x. Okay. In this particular case, we are trying to fit equation 11 to data S E and psi. So, if we go back to your equation number 11, that is what it looks like. So, how do you fit a straight line to this? This is a nonlinear relationship, or this is a nonlinear equation. Okay. And as you all know, we can convert a nonlinear problem into a linear problem. Okay. So, how do we do that? We can take log on either side and reduce this equation like this. Log of S E is equal to lambda times natural log of psi b minus so this whole thing, let us say, is your capital Y, and this whole quantity is your C, and psi is your x, let us say this is your x, and so then this becomes your m. Okay. So, we have reduced this equation in the form of y is equal to mx plus c. We have the data in terms of S E and psi. So, what we can do is we can either plot it or find the values of slope and intercept using the formulas which we have, and I do not want to go into the details of those. Okay. So, that way we will be able to determine what the parameters which are, what are the parameters? One of them is the lambda and other will be the psi b. Okay. We should be able to find it out once we know the values of m and c. Okay. If we try to look at this relationship, it looks like this. Okay. Psi in centimeters as a function of soil moisture content, or in the form of effective saturation S E. Okay. I am not going to put the numbers here, you can see it in the book, and it looks like this. It will appear as a straight line, and these different curves you see correspond to different value of lambdas, or these curves or lines for different lambdas. Okay. So, once we have established this relationship, we can find out what is psi as a function of S E or theta. Okay. Once we have that, we can use this relationship in the Green-Empt equation as a function of theta. During a rainfall event, as the time elapses, the soil moisture content changes in the soil, and we can use the modified values of S E and psi. So, this was about the psi. Okay. The other parameter of the Green-Empt equation is the permeability or the hydraulic conductivity. Okay. We will not go too much into the details, and except that fact that many researchers have worked on trying to find out how the hydraulic conductivity changes during a rainfall event in the unsaturated zone, and one of them is Bauer in 1966 showed that the effective hydraulic conductivity or effective K for unsaturated flow for unsaturated flow is approximately half of the corresponding K for saturated flow. Okay. So, as far as this course is concerned, we are just going to say that the hydraulic conductivity in the unsaturated zone is approximately half of the saturated hydraulic conductivity. That is what the research has shown, and the relationship of this hydraulic conductivity as a function of time or as a function of theta is beyond the scope of this course, although there are many studies that are available. Table 4.3.1 in your Chow's book gives you the values of various Green-Ampt parameters, okay, for different types of soils. All right, that is sand and clay and gravel and so on. Okay. So, this is about the Green-Ampt equation, its derivation and various types of parameters. Okay. The next thing which we are going to look at is the application of the Green-Ampt equation when you have soil which consists of more than one type of soil, or soil stratum consists of more than one layer. All right. This is called the two-layer Green-Ampt model. Two-layer Green-Ampt model. Okay. So, if you look at the field situation, this is your ground level. Okay. Then you have two different types of soils. Okay. The first one close to the ground is, let us say, consists of some soil which has hydraulic conductivity K1, suction head psi 1, initial moisture content represented by delta theta 1, all right, and its depth or height is, let us say, h1. Okay. Below that we have another soil which is K2 is the hydraulic conductivity, which has a different soil suction head and initial condition there may be different, okay, and its height is, let us say, h2. Okay. Now, we will look at this two-layer Green-Ampt model under certain assumptions, and one of them is that K1 is greater than K2. Okay. That is to say, for the upper layer is saturated so that water goes into the lower layer. Okay. And also we define the certain length L2 which is from this interface L2, this dashed line, and what is L2? L2 is the depth of the wetting front. Okay. Depth of wetting front means what? The upper layer is completely saturated, that is to say, the wetting front has completely penetrated the first layer and now it has gone into the second layer. Okay. And L2 is the depth of that wetting front from the interface between these two types of soils. Okay. So, in other words, we say that the limits of this L2 are such that it is less than H2, but greater than 0. Okay. So, that it is in the second layer. Okay. and this, let us say, let me define this as the wetting front. Okay. Now, with this conceptual or with this schematic, what we can do is we can write down the continuity equation, momentum equation, and combine both of them. Okay. We can carry out a very similar analysis which we did for the single layer. Okay. We are not going to do that. Okay. We will write this equation directly, the final resulting equation. So, what we will say is that using a similar analysis or method which we had described for a single layer, it can be shown that your small f, which is the rate of infiltration, is going to be equal to K1 K2 over H1 K2 plus L2 K1 times psi 2 plus H1 plus L2. Okay. This is your equation number 12, and once we have found small f, we can find out capital F, and remember that all of these are function of time. Okay. We are trying to find out the rate of infiltration and the cumulative infiltration as a function of time. This is equal to H1 delta theta 1 plus L2 of your delta theta 2. Okay. And this is your equation number 13. Okay. So, let me put these in the box, both of these equations, which represent the Green-Empt equation for a two-layer model. All right. So, if we have a field condition in which there are more than one different type of soil, then still we can use the Green-Empt equations or Green-Empt method to find out the infiltration, and we can use this equation 12 and 13. Okay. You can easily see that it should be very easy to extend this concept if we have more than two different types of soils, or 3 layers or 4 layers, or maybe more than that. Okay. Similar analysis can be carried out, and we can find out the equation, or we can extend this analysis to 3 layer or 4 layer. Okay. What do we do if there is only one layer? Then we just need to consider what we had just derived, okay, for a single layer. Okay. Now, we will move on further and look at a very important concept when we talk about the Green-Empt equation, okay, and it is the concept of what is called ponding time. I think I said earlier in one of the classes that any infiltration equation you take, whether it is Horton's equation or it is Green-Empt equation, they all give you potential infiltration. Okay. What does that mean? That means that there is sufficient amount of water available, or there is a ponding depth on the ground. Water is ponded on the ground to certain depth, and lot of water is available for infiltration. Okay. Under those conditions, whatever we obtain using these equations is equal to your actual infiltration. Okay. So, one of the basic assumptions of this Green-Empt equation is that there is ponding available. Okay. Knowing this, now when does the water start to pond? Okay. Initially, let us say the catchment is dry, rain starts to fall. Okay. The time up to which the water will start ponding will be different for different types of catchments, or it will be different in the same catchment for different types of soil, for different types of climatic conditions, rainfall patterns, and so on. Okay. So, it is very important to determine or find what is this ponding time, so that we can use this equation after the ponding has occurred. Okay. So, let us first define what is the ponding time. It is denoted as Tp, and the ponding time is the time elapsed Ponding time is the time elapsed between the time rainfall starts or begins and the time water begins to pond. Okay, on the soil. Okay. So, what does it mean? Let us say the rain starts at 8 a.m. or 8 o'clock in the morning and the water starts to pond, let us say at 8:20 a.m. or so. So, you have 20-minute duration in which the water completely penetrates or infiltrates into the soil. It will take the all of the water, and then water will start ponding on the soil surface or on your garden or in the lawns. Okay. So, that is called the ponding time, and it is important to estimate the value of this ponding time. Okay. So, what we will do is we will try to estimate this ponding time using certain procedure, but before we go for the derivation of this ponding time, it is important to understand that before the ponding, okay, what is F? F is nothing but your I. Okay. Whatever rain is falling, that is infiltrating into the ground. Okay. Therefore, this I is equal to F. Okay. And after TP or after the ponding has occurred, your F is equal to what? The maximum possible or the potential infiltration rate. Okay. So, calculation of this ponding time is an extremely complex process. There are various researchers who have worked on this and tried to give the expressions. Okay. What we will do in this course is we will look at one method which is proposed by Mayen and Larson, and it uses the Green-Amt equation. The advantage of this is it uses the Green-Amt equation, which is a exact analytical solution of simplified version of the schematic. So, let us look at the Mayen and Larson's procedure which was given in 1973. Okay. What they did is they presented a method of determining or finding the ponding time. Which is denoted as TP using the Green-Amt equation. Okay. How they did it? They used three different important concepts. Okay. Some of them we have already looked at. So, they used three principles. In finding out what will be the ponding time. One of them we have actually already written, but let me do that again. For the time less than the ponding time, all rainfall gets or is infiltrated. It should be very easy to understand and see. We have mentioned this many times. Number 2 is that the potential F has some relationship with capital F. That is to say, you need an equation or expression which relates the infiltration rate with the cumulative infiltration. Okay, and we have that for the Green-Amt equation. Okay, so we are fine there. And then the third step is that ponding occurs when your F is less than or equal to I. What does that mean? Ponding will occur when the rate of rainfall becomes higher than the infiltration rate. All right. When the rain is falling at a higher rate than what the soil can absorb, that is when the water will start to pond. So, let us look at this concept, and before I move further, I would like to draw a sketch which gives the moisture content as a function of the depth. Okay. So, this is your depth in the soil, vertically downward direction, and this is your soil moisture content. Okay. So, if I draw three curves during the rainfall event at any three different times, okay, and if I tell you that these three curves correspond to three different times. Okay. So, on the x axis you have the soil moisture, and on the y axis in the downward direction it is the depth. All right. As you go down into the ground, the moisture content will be different. Okay. And we have taken three snapshots at three different times, and if I ask you, one is before the ponding occurs, one is exactly at the ponding, and the third one is at the time which is after the ponding. So, which curve will correspond to which one? So, if you look here, there are three curves. The moisture content is less than, for this first curve, this one, the moisture content is less than the maximum, which is, let us say, eta is the maximum. Okay. So, obviously, on this curve the time is less than Tp, because right at the ponding you have saturated conditions close to the ground. Okay. So, just when the ponding has occurred, that is T is equal to Tp, then on the ground you have saturated conditions, and as you go down the soil moisture reduces. And the third curve which you see here, this is for the time greater than Tp. Okay. After the ponding has occurred, what happens? The wetting front starts to move down, or the saturated zone starts to increase by certain length. Okay. All right. So, this one I can write is the saturation moisture content, which is equal to eta. Okay. So, coming back to this derivation of your ponding time, we are going to do this using the Green-Amt method or the Green-Amt equation of infiltration. Okay. According to the Green-Amt method, we have seen the relationship between infiltration rate and the cumulative infiltration is that small f is equal to k times of your psi delta theta divided by f plus 1. Okay. And let me number this equation as equation number 14. Okay. Now, what we are going to do is, we will write this equation just at T is equal to Tp. All right. So, at T is equal to Tp, if we write this equation, what is equal to small f? What is small f equal to? Okay. I think we have just written it in the last sheet. Just at the time to ponding, your, or just before that, what is f? F is nothing but the rate at which rain is falling, right. So, we can say that at T is equal to Tp, your f is equal to nothing but the rainfall intensity. Okay. And what is your f p going to be? Okay. If we know this, that the just at that time is equal to time to ponding, your f is equal to I, then what will be the cumulative infiltration at T is equal to Tp. All right. As you can see, it should be nothing but your I, which is the rate at which rain is falling, times Tp, right. intensity is centimeters per hour and let us say Tp is in hours. So, the cumulative infiltration will be nothing but I times Tp. Now, one thing we should understand here is that during this whole analysis we are assuming that the rate at which rain is falling or I is constant. Okay. During that time interval for an hour or 2 hours or whatever, the I is constant. If I is not constant, then this whole analysis will not be valid. Okay. So, under this constant rainfall intensity assumption, we are deriving this. Okay. So, now what we do is we just substitute these things in equation number 14. Okay. If we did that, then left hand side is F, which is we said is I, is equal to K times psi delta theta divided by capital F, which is at T is equal to Tp, which is Fp, and which we have said is I times Tp, okay, plus 1. All right. So, this is a simple equation and we can find out what will be the explicit expression for Tp. Okay. So, your Tp will come out to be from this equation as K psi delta theta divided by I times I minus K. I am not going to derive that, it should be very easy for you all to see this, to come from this equation to this equation. You can take this as an exercise and verify this. Okay. And let me say that this is my equation number 15. Okay. So, this equation 15 gives, that is your equation 15, gives the ponding time under constant rainfall intensity using the Green-Ampt infiltration equation. Okay. Looking at equation number 15, it should be very easy for you to see that your Tp is function of your hydraulic conductivity K, psi is the suction head, comma, delta theta is the initial conditions, and I. Okay. If the hydraulic conductivity is more, okay, if you are comparing let us say two different catchments, one has lower hydraulic conductivity than the other, okay, which one do you think will have more ponding time, or which catchment will take more time to pond as compared to the other one? Okay. Obviously, higher is the value of K, higher will be the ponding time, because water will infiltrate quickly into the catchment, okay, and Tp is directly proportional to K. Similarly, higher is psi or the suction head, higher will be the ponding time, because psi is appearing in numerator. Okay. What about delta theta? If the initial conditions are such that the catchment is already saturated, all right. If the catchment is saturated means what? Let us say your, what is delta theta? You want to look at, it is eta minus theta I. Okay. If theta I is higher, delta theta will be lower. Okay. For a higher theta I, delta theta will be lower, so that your Tp will be lower. Okay. So, because of the negative sign, it is an inverse relationship. Higher theta I, lower Tp, lower theta I, higher Tp. Okay. It should be easy to see that. What about the rainfall intensity? Okay. If you consider a situation in a catchment when rain is falling at a very high rate as compared to other case or other time when the rain is falling at a smaller rate, in which case you will have higher ponding time. Okay. obviously one which has slower rainfall. Okay. Higher the rate of rainfall, quickly the water will pond and time to ponding will be small. So, it is easy to see that the equation which we have derived intuitively makes sense. Okay. So, let us move on further from here and say that I already said that on the previous page that your time to ponding is function of many parameters, which is k hai, psi, delta theta and I, all these 4 things, wherein your k and psi are the function of soil type. So, the time to ponding depends upon the type of soil in the catchment. What is delta theta? Delta theta is the function of your theta I and also the soil type. Okay. So, it will depend upon the initial conditions, and I of course is the storm characteristics. So, you see that the time to ponding will depend upon all these things, that is soil type, the initial conditions and also the storm characteristics. Okay. Now, the next thing which we are going to look at is how do we find infiltration after ponding. That is to find infiltration after ponding. Okay. That is for the time when time is more than Tp. Okay. Well, we know that from the Green-Ampt equation, this is true, this relationship. Okay. Let me number this as 16. This is nothing but our Green-Ampt equation for a single layer. Okay. Now, what we do is we can write this equation at T is equal to Tp. Okay. That is to say, using this equation, at T is equal to Tp, what do we get? At T is equal to Tp, your F is Fp minus psi delta theta natural log of 1 plus Fp over psi delta theta is equal to k times what? T is Tp. Okay. So, if I say that this is number 17 and then I subtract 17 from 16, that is 16 minus 17 will give me what? Will give me F minus Fp minus psi delta theta, and in the brackets you have natural log of psi delta theta plus F over psi delta theta, one part, and if you subtract the other one, you will have natural log of psi delta theta plus Fp over psi delta theta. Okay. So, this is on the left hand side, and on the right hand side you will have k times T minus Tp. Okay. You can simplify this further to obtain F minus Fp minus psi delta theta of your natural log of psi delta theta plus F over psi delta theta plus Fp, okay, is equal to k times T minus Tp. So, this is your final form of Green-Ampt equation, which can be used after ponding. Let me number this as 18. Okay. So, equation 18 gives you the infiltration F at any time after ponding. Okay. It involves Fp. Fp is nothing but I times Tp. Okay. Once we have determined what is time to ponding, Tp, all right, using this equation which you have just seen, we can find out what is Fp, we know what is Tp. Okay. Everything else in this equation is then known except capital F. Okay. And we can find out capital F using certain numerical iterative technique. All right. Once we have done that, we can find out small f. Okay. So, this is the procedure for finding the or using the Green-Empty equation rather. Okay. I think I would like to stop at this point of time because I am at a good stopping point, and in the next class what we are going to do is we will look at a few examples of infiltration or the use of the infiltration equations. Okay. So, we will look at the example of the Green-Empt or maybe the Horton or some practical problems in which we will use these infiltration equation to solve certain problems. Thank you.